Welcome back, chat. Pansinin Mo! Today, we are going to start Chapter 4. And Chapter 4, we are just going to keep building up our repertoire of understanding of what causes change in motion and things like that. That is way too fine. But in Chapter 4, we will be looking at forces. Now, specifically, we're going to be looking at the easy version of this first, right? It makes sense to build in and then start building it up. We're going to be looking at forces, and for this chapter, we only work in one dimension. Okay, forces in one dimension is going to be our focus throughout the next several lessons. As we go through, today we get the privilege of starting Chapter 4, Section 1, where we will be discussing specifically force and motion. Okay. Can you guys create forces? I think so, right? If you all have muscles that work, you're probably doing it. Even if you don't have muscles that work, you're doing it right now, which is pretty cool. What's a force? How would you define it? We all have an idea of what it is, I imagine. How would you define it? Give it like 30 seconds with your neighbor. Let's see what you come up with. Without a book definition, although Barsega, I appreciate that you follow along in the text. What's a force is the question at hand. 30 seconds. All right. Huggins, how would you define a force?
I wouldn't right now because it's too early.
So what if I said you got to try something? What's your first thing that comes to mind if you had to explain to somebody what a force is? Energy. I'm okay with that idea. It's a good kind of entry point with that. So energy is a interesting thought, or an interesting thought rather. Anybody have a different definition? I don't know what I was hearing. It sounded like there might have been a cat meowing or something. I don't know. I saw somebody do this with a arm extending motion. Is that a way to create a force? Like, I can create a force? Yeah, for sure. There is an issue that I have with this because it implies that force must come from me, right? Which I can create force, but check it out. I'm not going to push this. Still fell. So something must be happening. Did that push down? I don't think so. It pulled. What pulled it? Gravity, and gravity's a force, right? So as we look at these things, we're just going to sneak in. Our first main section is force, but we're just going to sneak in with a definition right off the bat. Now, capital letters and stuff matter. When we use a capital M for mass, it drives me crazy, but it hasn't burned us yet. There's a possibility that it will. If you got to write and choose how we're going to write down a force, any gut feelings of what you'd want it to be? Force. Good, it's an F. Okay, boom. All right, now as we talk about force, we're going to have the simplest possible definition for it at this point in time. We're going to say that a force is simply a push or pull on an object. A push or pull on an object. That's it. Now, with this, if I wanted to apply a force to this to move it, I can, right? How hard do you think I need to push to move this table? So not that hard. So if I pushed with, like, I don't know, we don't have a good unit for force yet, but we will. If I pushed with 100 pounds of force, you think I could move this? Easily? Everybody think that I could probably move this easily with 100 pounds of force? So if you're telling me if I push on this with 100 pounds, it should move, right? Ah, shucks. It moved because I went in at a goofy angle initially, but there's something more specific we need, right? You need to tell me how hard to push, but what else? Ooh, what direction? So we need a size or a magnitude and a direction when we talk about a force, which means, unlike temperature, this is a what sort of quantity? If it needs something, size, magnitude, and direction, what do we call those things? It's a vector. So check it out, quick follow-up. Force, F, and we're not going to stick with the notation consistently, but just so you guys are aware, force with that little vector arrow above it is a vector, which just implies, and I'm going to use my little fancy implies thing, every vector has two values. What are they? Magnitude and direction. Okay, every single force that we deal with, just like velocity or acceleration, we need a magnitude, how large is that value, and we need a direction. Now, this bugs me that your book does it this way, but I'm going to follow their lead. One more follow-up comment. Force has the unit newtons, and this drives me crazy that it's not capitalized here. Newtons, N, capital N for newtons. Okay, we measure force in newtons. That's a unit. F is the label. Okay, now as we're dealing with this, if I apply a force to something, it could move, right? Does it have to? What do you guys think? If I apply a force, does something have to move? There's probably a good example. I pushed downward on this table a second ago and it didn't move, right? Or this one I can push sideways, but I'm not stronger than this wall. So we have an issue with this. Now, it won't always move. That's, I hope, like clear and obvious. Can it move though? Yeah. So when we look at stuff, here's the important idea to remember. And there's going to be a lot of important ideas, but we're going to look at a very specific case. And I'm going to switch colors just as I'm doing a subsection. Let's go green. We're going to look first at unbalanced forces. Now, something as simple as in front of you there's texts or something on your desk. If you barely touch it and just really lightly push on it, it doesn't move. Now, I'm applying a force, but it's not moving. Why? So I'm pushing to the right, for example. My book isn't moving, which means something must be opposing me. And there's a lot of answers that I might be expecting here. The weight of it might have something to do with it. Anything else? Friction. Now, as I push to the right, friction is stopping me from moving, yeah? Which means friction must be pushing me which direction? The opposite way, right? Correct? Sorry, I shouldn't use right and left and all that. Now, as we look at this, it all comes down to a really easy way to think about these. If we have an acceleration, which happens with us, it must be caused by something. So we're going to make the following big statement. All acceleration results from unbalanced forces in the direction of acceleration. Okay, big key point here, acceleration. Really important idea, and I wish that I had this on video, but unfortunately I don't. I have a ball, and a marble specifically. Notice there's a small distinction that everybody needs to be aware of. I'm going to roll this ball slowly. Okay, so right now it's not moving. I'm going to apply a force to it, and it's going to roll down, right? Now, it'd be weird if this thing just rolled forever, in my mind. But I want everybody I'll call out a point, and I want you to tell me what's happening with the acceleration. As it's going, the force is pushing on it. Sorry, I didn't call out a point. I got too excited about the idea. Which way was the force acting as soon as I released that? So it was going toward me, right? So notice, really important idea here. In the direction of acceleration, not motion. If I'm stopping my car and I'm approaching a stop sign, the acceleration is going in the other direction to slow me down, backward from the way I came. Not the direction of velocity necessarily. It could be, but it's the direction of acceleration, and that's a super important idea. Okay, I'm going to pick that up or else I'm going to slip on it later. Now, beyond this, your book goes into super detail. I don't think we need any more than that just to get the point across. We're going to start dealing with problems where there's multiple forces within. So we need a good way to talk about these things. So we need to define for ourselves the idea of a system. A system. And I'm going to write in physics because this is such a common word in like other fields that I want to, obviously we're in physics, but I don't want you to get confused in your head. Now, when we talk about a system, we need to be really specific, and we'll get into more details regarding these over the next few minutes. But when we look at a system, all that we're really concerning ourselves is all of the objects of interest with respect to force. Now, in this situation, there's a few different examples. I have a textbook on my desk, and most of you guys do as well. There are forces acting on your textbook as it sits on your desk right at this point in time. When we think about this, and I'm going to draw like a really lame table. You guys can draw this if you want to, but check it out. There's an awesome table. And then I'm going to use this as my book. Here it is. It's a thick book. Cool. There's a book sitting there. It's not doing anything. I'm making a claim that there's some forces acting on this. Can you guys tell me what they are? So gravity certainly acts on it. So if I just want to highlight this over here, I'm just going to put a dot right next to it. Gravity pulls or pushes this thing. It pulls it downward. So I'm going to make my vector, and I'm going to do it off to the side just so I can label a little bit cleaner. I'm going to make my vector pointing downward, and we need to be really specific with how we label stuff and talk about things. This right here is the force of gravity. I'm going to say F sub G. Now, I know for a fact that this is not unbalanced, though, because if we had unbalanced forces, I would expect it to be accelerating in some direction. It's not right now. What balances this force? Why isn't your book falling down to the center of the planet right now? The table. What's the table doing? So it's stopping it, but it's doing more. If we think about that, it's stopping it so that our forces are balanced, right? Because unbalanced would result in some sort of acceleration, which means it's a weird idea, but if I go from the same point, the exact same size, exactly opposite direction, and this one we're going to have to use a little bit uglier subscript, you agree that there's also the table pushing up on the book? Like, it must be, right? Because otherwise we would get motion out of this thing. Now, in this specific example, I'm looking at all the objects of interest with respect to the force. What is the system, the object of interest that we're looking at here? In this particular example. There could be more than one, just so you're aware. The book is certainly one of them, right? We're asking questions and thinking about the book. But there's another actor in this. Something else that must be accounted for that we've already identified. So gravity. So that's a force in there. It's not the object itself, but I like where your head's at. We'll talk about that in a minute. So the book, where's the book setting? It's in contact with the table that's also applying a force, right? So if we look at this, I'm just going to highlight it. I'm going to circle it in yellow, I suppose. This right here is our system. As we look at these, they can be more challenging to pick out. In this situation, it is the book on table, or book and table, but I want to be more specific. Now, alternatively, if we had, for example, a ball or a marker just falling through the air, and I stopped time, which I can't really do, I don't think. Stop, nope, can't do it. As it was falling, what was the system there? The only object of interest as this marker was falling downward. It's just a marker, right? There's no other objects dealing or creating force on this thing whatsoever. Our system is just that. Now, if I had this connected to a string, or for example, if I'm looking at this marker as my topic of interest, there we go, and it's sitting here. Is it connected and physically in contact with the external world right now? So if I were to start looking at forces here, it's almost the same as the book on the table, just looks a little bit different. If I want to consider the forces that are happening right where that marker was a moment ago, we have a system containing the marker itself and this string that I'm using to hold it up. Okay, there are other forces acting on it. There's some crazy, I don't know where that went. Weird. Okay, I'll find it later. As we go through these systems, we'll get more and more specific, but rather than talking a ton about them right now, I'd rather just be as concise as possible. Cool. All right, kicking forward a little bit more, and at the start of a new chapter, just a heads up, there's a lot of vocab and just kind of like laying groundwork stuff. So if this gets boring or we need a quick break, just let me know. Cool. So, as we go through here, I'm going to talk about a few of the basic types of forces. Okay, this is not an exhaustive list. I want you to be well aware of that. There are more than we're going to list right now, but we're just getting into the woods a little bit, so we'll make sure it's nice and chill, hopefully. Okay, the first of these, forces. We said a second ago that the table was applying a force to your book, right? Now, if I do this and I hold it right here, and even if I drop it right now, while it's in the air, is the table applying a force to this? So you say yes, why? So you're absolutely right. Once it hits, it does. Before that, though, does it? No. So when we're looking at these, the first type of force that I want us to make sure that we're aware of, and this is the easiest, is what's known as a contact force. This is one of the times that your gut feeling for what this is, that felt clunky as I said it, your intuition for this definition is going to be perfect. To have a contact force, what do you think me and the object that is being forced have in relation to each other? That's a weird way to word it too. Oh my gosh, they must be contacting each other, yeah? So we're just going to be more specific. We're going to say that this is caused by external world. Caused by external world. In physical contact with the system. Okay. You can thank contact forces for your ability to get in your car and start moving, to turn, all of those things. The greater the friction there, the better it is, right? We all know that if your tires have no tread, you're in trouble come wintertime. Like, there's a reason for that. Your contact forces are related to friction, depending on the situation. Okay, give me another example of a contact force. Friction is a contact force. If a skydiver jumps out of a plane, do they experience a contact force? Pick a side. I'm going to give you 20 seconds. Does a skydiver experience a contact force while they're falling through the air? 20 seconds starting now. Like your class photo? I don't think so. I don't know. Yeah, for the yearbook? I don't know. Have you heard anything about it? My guess is no then. Usually that's done elsewhere. Have you guys even talked about what you want as your senior photo? Maybe. I would check with your advisor. Anyway, skydiver, contact force or no? So I heard yes, and I saw you saying no. That's okay. Why yes? Air. Are you touching the air right now? For sure, right? Now, if you cup your hand and do this, you can't really feel it in the air, but if you're in water, would you notice it? Now, they're both fluids, which is a weird idea. We don't usually call air a fluid, but it is in the physical sense, just less thick and dense. Now, as we go through, air resistance is your contact force, right? If you were to jump out of a plane, wouldn't be a plane anymore. If you were to jump out of a ship in space, then no contact force, right? Okay, in contrast with that, speaking of space and stars and wars, we also get field forces. I know we weren't talking about wars, but I can't talk about force without thinking of that. Which if you guys are Star Wars nerds, apparently not, but okay, all right, okay. Field forces. Okay, field forces. These ones, we have probably a few. Star Wars isn't real, I don't think. I don't know. I'm pretty sure it's not. Can you identify a field force? and we'll contrast it here in a second. If contact force has to be physical contact with whatever system you're looking at, what do you think a field force might be? Good. It is exerted without what? One more time. Contact. Okay. This one's a little bit more challenging. Can you guys identify any field forces? So a force field in sci-fi, definitely. Magnets. Awesome. So we'll do a couple here. We didn't do it EG for the contact forces, but I'm just going to say electromagnetism. You can just write magnets if you'd like it more simple. Electromagnetism is a field force. Do you guys know what a magnetic field looks like? You can't see them. Not naturally anyway. Probably don't. They're awesome. For our brain break, maybe we'll see what one looks like. Cool. Can you name another? Ooh, the Earth does have one. Now, the Earth also has a huge electromagnetic field surrounding it. But there's another one that's always acting on us everywhere, no matter what. Gravity is another of these field forces. Now, there are more that exist beyond this, but they're nice to think about here. I'm just going to put ... The last one, we won't see this section, I don't think, of this chapter, but there is one more type of force that's called a fictitious force, which is terrible language. There's nothing that really causes it other than your relationship to movement. So centripetal force, there's nothing that's really causing it. It's the motion that's causing it. No physical object or field that's causing it. If you ever been in that carnival ride that sucks you up to the sides, like a big centrifuge, if you know what I'm talking about, where it's really hard to sit up, like, yep, there's nothing really causing the force other than your position and movement, which is a neat idea. We will talk about those more later. Okay, so for our purposes, we have contact forces, field forces. One more little comment, and then we're going to take a quick brain break, and hopefully I know exactly where the thing that I want to show you a magnetic field with is. Last little piece we have to talk about. We have a system, which is all the stuff that's connected to the force that we're examining. We have the forces that might be acting on it, whether they're contact or field. And finally, we have our agents. Okay, an agent. When we're dealing with this, this is where philosophy and physics may blend a little bit towards the deeper levels of understanding. So when we talk about the agent for a force, right now, I know that this thing is being pushed down by gravity, or pulled down, I'm sorry, by gravity. What causes that gravity? The Earth. Would you guys agree? So in that situation, the agent is the Earth, or the mass of the Earth. So when we're looking at these, we'll just say that agents for our purposes are the specific and identifiable causes of a given force. Okay. We are going to pause this for just a brief second. Could you guys use a short brain break? Okay. I want you to discuss. I'm going to pop over to the lab to see if I can find something. Magnetic fields, I guarantee you've talked about them, whether it was in physical science or earth and space science that you guys took in middle school, freshman year, somewhere in there. I want you to see if anybody in your vicinity recalls what magnetic fields look like. I'll give you a second. We'll pause it so it's not awkward silence.
We are recreating a tremendous video from Reddit a few years ago of iron filings flying up in the air, visualizing a magnetic field around a magnet. Ready? Yep.
Did you guys catch it?
Oh, yeah, you can clearly see it there. See the curve.
So you can tell down here you're starting to already get the field, and it is that curvy shape you were talking about. Up here you can see that same curvy shape happening. We can see the magnetic field forming.
There must be a cut-off point where the weight of the iron filing is falling.
Now, in case you guys have never seen it, that's pretty cool. I hope you found that cool as well. Have you guys ever seen ferrofluid? Okay, so check this out. Awesome. Here's ferrofluid. And apparently some strange noise. So this is magnetic fluid that they have put on a strong magnet. Now, it has a crazy shape, right? All you're seeing is that each one of these little spikes is following along a magnetic field where the magnetic strength is stronger, so they are directing themselves in the orientation of that magnetic field. These things are all around us all the time. We will have a whole chapter on magnetism and stuff where we'll play with magnets, and I'll have time to find the other thing that I was going to use to demonstrate this. Do you want to watch this for a minute? There's cooler videos than that. But we're not going to watch all 3 minutes of it, but hopefully they'll do something cool. I just want to watch it go crazy. Ooh.
There's a very weird liquid, this. On the scale of 1 to of weirdness, this comes at about 433. Is it the blood of some strange machine, you ask?
Really hard to make or expensive to make. I know there's some ferrofluid here in the school. I'll see if I can't track it down by the time we get to our stuff. Cool. All right. So continuing on. We have done quite a few problems, at least with simple motion stuff and relatively simple. I haven't fixed my board yet, but I'm going to keep those up there. As we go through things, quick question. How many of you guys have drawn pictures to help with a problem? So roughly half of us. As our problems get more complex and there's more stuff going into it, I would strongly advise it would be a good thing to get in the habit of. So when we are dealing with pictures in here, specifically dealing with forces and things like that, we're going to use what are known as free body diagrams. So I'm going to try to sneak it here, and I'll move it if I have to. Okay, when we're dealing with stuff, we've already seen object or particle models where we just look at simple motion and say, hey, look, here's how it's moving and with relation to time and things like that. This idea will be with us for the rest of the year. We're going to give ourselves free body diagrams. Now, this thankfully, for me, maybe not for you guys as much, but thankfully does not require a large degree of artistic ability. As we're thinking about free body diagrams, all that these are is a physical representation, which is physical in the sense that we draw them, a physical representation that clearly identifies. I'm just going to say that identifies. And then I'll wait a second to tell you when to turn pages. But we have to identify everything that's important in any given problem, especially with respect to force. It has to identify, the forces. So all forces. It has to identify the agents. Now I'm going to do agents like this because maybe it's one agent, maybe it's multiple. And the system. Okay. We need to have a clear idea of what's going on, what's the forces, what are the agents, and what's the system that we're actually dealing with. Okay. If you want to turn your page, I take my notes double-sided, just if you guys have never seen that, I do half and half. We're going to talk about the guidelines. On my page, they're this. If you can see it, that section of my page are the guidelines for drawing these free body diagrams. If you are at the bottom of a page, I would possibly suggest turning it over before we do this. Cool. And I'm just going to move it up here. Okay. As we're dealing with our free body diagrams, this is a nice kind of list to have just ready to reference if you need it, because drawing them can be better than drawing an actual picture, but they're easy to get goofed up with. So we're going to go through some guidelines. Yes, sir?
It's a physical representation that identifies
Forces, agents, and system. Sorry, I cut you off. That's my bad. Okay. If I just say guidelines for drawing, based on the way that this is outlined, do you know what we're drawing? What? Angel? Free body diagrams, that is correct. Okay, now, first and foremost, if you are feeling artistic or having a picture of it with actual stuff drawn in would help. I would strongly encourage it. Sometimes I will, but I don't put a whole lot of effort into doing this. So as we're doing it, I just want to make the first comment. If you're a picture drawer, that's cool, but I need you to draw this free body diagram, draw separately from any sketch or picture. Draw separately from picture. So I am actually going to write it here because it's going to bug me if it's not. You don't have to. Okay, so right off the bat, if you're dealing with a person or you're dealing with a brick or an elephant, doesn't matter. I'm going to use the same drawing in a free body. What's the easiest thing to represent an object? What's the easiest way to draw any arbitrary object? Bar-Sega. We've used it before. Instead of drawing like a guy on a skateboard, which might be a dot, we're going to use a single dot. So use a dot to represent, I'm just going to write rep for represent object. Okay, easy. We just have a single dot, piece of cake, much like this one. Cool. Beyond that, we need to have our forces drawn on there somehow. And we're going to follow a convention that is going to feel strange at first, but I promise it'll get easier. We're going to use a vector, or use, and I'm going to specify force vectors that originate at the object. Now, this is a weird idea when we first think about it, but I'll show you what I mean by that. I'm going to draw it in white over here. You don't have to draw it, and I'm going to draw a picture with the actual stuff. Let's say that we have this happening, and we have a person pushing. So they're going to push on this box pretty heavily. And then somebody over here pushing as well. Okay. I don't know why they don't have shoulders, but that's okay. As we're looking at it, if they're pushing, obviously one or neither of them will win, right? And it's really natural, if this person's pushing, it is supernatural to say, hey, look, they're pushing like this, and this person's pushing like this. Do you guys agree with that's natural? Here's the weird part. Even if I only have one person, does this still feel natural? Okay. However, when we do free body stuff, it looks like he's pushing because that's the context. This is my picture. If I were doing my free body diagram, this one person that is the only person in this object at this point in time, here's the center of my object, here's what they're doing. That's F1. As we deal with it, it doesn't matter if it's being pushed or pulled realistically. All that matters is the direction of the force. Draw it from the center of your object. If the other person were pushing from the other side, I would just simply draw it here. Okay, they all originate from that object that we're focusing on every single time. It's a weird thing to get used to, but with the free body diagram compared to a picture, I think it feels a little bit more natural. Okay, beyond that, and I'm going to say at the object and move away. Okay. Furthermore, vectors, when we draw them, they are directed line segments, which it just looks like an arrow that has a specific magnitude and direction. As we deal with these, we need to make sure that our vectors are drawn proportionally. Are drawn proportionally. With, and I'm going to pause there for just a second. If I say vectors are drawn proportionally, what does that mean to you? Let's see, I'm just going to go down the list. Tole, I haven't called on you today. So they could be the same length. If I have a force of 50 newtons and a force of 5 newtons, should my vectors be the same size? No. Do I expect you to get a straight edge and actually measure it to be 50 centimeters and 5 centimeters? Not even a little bit, but you should be able to very clearly see which one's larger. Like, try your best to draw them proportionally. I got a Red Bull something this morning, and it's delicious with cream. I don't know what it is, from the coffee shop. Just wanted to brag about that, so you know you guys don't have them. All right, with values, if known, and subscripts for context. Now, I tend to play fast and loose with my subscripts because I can keep track of it relatively well. It's going to get real annoying, but you're going to see F sub table pushing on book. Like, we're actually going to write all that out. I will try my very best to. I usually just use F1, 2, 3, 4, and so forth. But you want to be specific so you understand the context. All right, last little thing. If changing positive direction. And I'm just going to use my plus sign there. If you're changing the positive direction, other than the default, what's default is positive on a drawing? Which direction is this? Which one of these arrows, two of these arrows go positive by default? Can you tell me which ones? This is default positive. This is default positive, which means these are default negative, right? Okay. If you are going to change stuff, which it will happen, like there's going to be times when it makes sense, if you're changing the positive direction, clearly indicate it somewhere. Okay. Now, as we go through with these, let's do a small example here, and we're going to use this again later. I'll just make a different example. So here's what I want you guys to do. We'll do a quick example where we'll sketch, and then I have a suggestion. If I use this, FBD, I've never done this, but I don't want to write this over and over and over and over and over. What might this stand for? Anybody opposed to using FBD for free body diagram moving forward? Unless you can keep writing it and I can keep writing it if you really want me to, but I think FBD would be convenient for us. Cool. All right, here's what we have on example A. Let's say two people play tug of war. And I think it's actually tug-o-war with a apostrophe, but I don't know that well enough. Okay, one pulls with, let's say, 300 newtons, and one with 500 newtons. That's it. They're playing tug of war, two people pulling on a rope. I'm going to give you a moment. I want you to draw the free body diagram to the best of your ability. If you want to draw a picture, you can as well, but we'll come back together in about 20 seconds, 30 seconds, a minute, I don't know. If you're watching this on the road, feel free to pause it now, and you will see my picture in 3, 2, 1. First thing I want to check. Some of you probably drew a picture similar to this, and I'm cool with that, but I want to really think about this. What is missing from my picture? I heard two really quiet things. Labels. So what's labeled? Okay, so if we go a little bit further, I didn't specify, so it doesn't really matter. Let's say that this one, just purely out of arbitrary choice, is 300 newtons. That means this one would be 500 newtons. I want you to tell me what's wrong with my pictures. There's lots of stuff wrong, but one thing that you saw? I don't know who said it over there. Sean, what's wrong with this picture? The different directions. I'm okay with different directions because they're playing tug of war. Say it again? The origin is wrong, so definitely this is what I was highlighting. I hate this. Who does it look without the numbers? Who's pulling harder there? The other person. We need to make sure that we're proportional. Now, I didn't measure it out, but now it's a little bit better. But you had a different option and a different suggestion, Huggins. You said the origin. This is a beautiful picture. Like, great, and pretty near the peak of my artistic ability, just so you guys are aware. However, I didn't ask for a picture. We needed a what? We needed a free body diagram. So, there's other issues that I have with it, This is a great picture. And if you need to draw it to help make sense, that's awesome. But there's a few things that I have issue with here. If we draw the actual diagram, I don't really care about what's going on other than the forces in the object. What's the system right now? So the rope, anything else? So forces are certainly acting on the rope, but they're in contact with the physical world outside through where those forces are applied. My system are these two people and the rope itself, along with realistically the ground that they're on. Like all those are part of the system. Now, if I wanted to draw this picture with a free body diagram, I'm going to simplify it so much. Check it out. Here's the center of the rope, or the rope. If you'd like to think of it that way, it's easier to think of it as the center of the rope. One person's pulling this direction, and I'm going to switch colors as I do this. One person's pulling this direction with 300 newtons. Now, I'm going to be real specific. I'm going to call this F1. And I will specify 300 newtons. Okay, the second person pulls F2 for a second, and they pull harder. I'm going to go to right here. Now, I have graph paper, which makes this easy. I'm going to call this F2, but there's something specific that needs to happen here. I'm going to leave a blank space for a very particular reason. 500 newtons. I have it mostly clearly labeled. There's no context. I'm okay with that. Why did I leave that awkward space, though? Say it again? Yeah, I need to know if that one's positive or negative, because if they're both positive, something's wonky here. What should it be, Nick? 500 newtons, positive or negative? Good. Could I make it positive if I wanted? But I would just have to include that this is a positive. And if I include my signs here, then we're going to be able to specify it in that way. Now, you guys will find as you're drawing your free body diagrams, oftentimes the stuff that you're going to draw and label on your free body diagram is going to overlap a lot with your givens. It's okay. I'd rather you spend the extra 30 or 45 seconds drawing it and labeling it to make sense of the situation rather than just trying to jump right in with a poor sketch and spending 15 minutes trying to solve it and then being wrong and having to come back and do it anyway. All right. Now, as we continue on, last little thing that we're going to look at starting today, we have a free body diagram. It's awesome, kind of, sure. Last little piece, and we'll go with this lovely peach or salmon color. We are going to start looking at how does one actually go about combining forces. Now, we are not in a math class, unfortunately. There's a lot of math in here, but it's not a true math class, which means when we're dealing with combining these forces, we may not take the same approach that we will in a pre-calc class when we do vector stuff, because we do deal with vectors in pre-calc. I think you guys probably did a little bit in Algebra 2, I would guess. Maybe not. It'd be when you did systems and matrices, if you remember doing all that fun stuff. Anyway, when we combine forces, the main idea, and this is super duper important, we're going to talk about this idea of net force. And that should have been caps, because this is a vocab. I will fix it. Net force is going to be like the most important thing that we can calculate, and that we will calculate on a regular basis. I spoke a moment ago about the subscripts. When we talk about net force, we literally write F sub net. This is our net force, F net. Now, anybody here work for money and you pay taxes? Okay, when you get your paycheck, you're probably going to see there's a gross amount, not like ick, but gross as in total, and there's a net amount. Your net is always less than your gross. Why? Taxes. The tax man comes and gets it. Now, as you're dealing with this, the same idea works here. To you find your net income, you take your gross pay, all the total pay, and then you add it with the negative taxes that are taken out. Now, you could just say subtract the taxes, but I want to think of this idea of adding. We're going to say that net forces, super easy to calculate. It is the sum of all forces acting on a system. Okay. Last statement, and I lied. We will start right here tomorrow. Do me a favor. Tomorrow, I want you guys to bring your computers. Cool. All right. I don't know if I mentioned it yet, just in case I haven't. Cowboys won.